We're looking at exponential functions and their derivatives, and first we're going to remind ourselves of the graphs of exponential functions. Consider f of x equals b to the x. The base is b, the exponent is x, and we consider bases that are positive, so b is greater than 0, but we don't consider bases b equals 1, because that would be b for boring, and x, the exponent, can be any real number. We'll look at the graphs of two cases, one where b is greater than 1, and one where b is a positive number but less than 1. For b is greater than 1, we see a curve that exhibits exponential growth, and if the exponent is 0, then the output is 1, and so all exponential functions of the form f of x equals b to the x will go through the point 0, 1. Because this sweeps up to the right in the first quadrant, we can see that the limit as x approaches infinity of b to the x is equal to infinity. And because we see that this is asymptotic on the left with the x-axis, we see that the limit as x approaches negative infinity of b to the x is equal to 0. In the case that b is between 0 and 1, we see the graph shoots up to the left in the second quadrant and then becomes asymptotic with the positive x-axis. And this is, of course, exponential decay, and it's also a reflection about the y-axis of the first graph that we looked at. Again, we see that this curve goes through the point 0, 1, and then as we look up in the second quadrant, we can see that the limit as x approaches negative infinity of b to the x is equal to infinity, and then being asymptotic with the positive x-axis indicates that the limit as x approaches infinity of b to the x is equal to 0. These are true for bases less than 1. That was our quick reminder about exponential functions. We're now going to go straight into their derivatives. Using the definition of derivative for f of x equals b to the x, f prime of x is going to be the limit as h approaches 0 of b to the x plus h minus b to the x divided by h. We can factor out a b to the x. We're left with the limit as x approaches 0 of b to the x times the quantity of b to the h minus 1 over h. And that should have been the limit as h approaches 0. The point there is, as h approaches 0, b to the x is unaffected. And so as a constant, we're going to pull that outside of the limit. So we get b to the x times the limit as h approaches 0 of b to the h minus 1 over h. That limit that we have here, we are going to revisit in a future section. Our takeaway is that since this limit is a constant, assuming that it has a value, that the limit exists, what we see is that the derivative of an exponential function is a constant multiple of the exponential function. Not only that, but since b to the 0 is equal to 1, the limit can be rewritten as the limit as h approaches 0 of b to the h minus b to the 0 over h minus 0. And here I've just replaced the 1 with b to the 0. And then I added another term, h minus 0, just in the denominator, because that allows us to express the derivative f prime of x as f prime of 0 times f of x. So here, this is the definition of derivative, and if we were to replace h with x here, then this is the expression for f prime of 0. And so just to bring things together here, I'm going to put this in blue and say it's not only a constant multiple of the original function, this derivative, but the constant multiple is the derivative itself evaluated at 0. Again, if the limit exists. So let's explore that limit a little bit. We're going to consider two cases, b equals 2 and b equals 3. The limit as h approaches 0 of 2 to the h minus 1 over h is an expression that we can find an approximation for by using a table of values. So we'll consider h equals 100th, 1,000th. 1 is at 1, 2, 3, 4, 5, 1/100,000th, and then 10 to the negative 7. And calculator values for this will be, for h being 100th, 2 to the h minus 1 over h is 0.69555. When h is 1,000th, we have 0.693387. When h is 10,000th, we have 0.69315. Same value when we have h is 10 to the negative 7, to 5 decimal places anyway. The thing I want to say here is this limit, as we look at the values in the table, seem to be approximating somewhere around 0.69. And all I want to say about that at this moment is that it's less than 1. Now the limit as h approaches 0 of 3 to the h minus 1 over h, same process. I will cut to the chase so you can verify using a calculator. We get that this is approximately 1.1. And again, what I want to point out here is that it is greater than 1. So when the base is 2, I have a limit that is somewhere less than 1. When the base is 3, I have a limit that is somewhere greater than 1. It is reasonable to expect that there exists a number b between 2 and 3 such that that limit that we're talking about as h approaches 0 of b to the h minus 1 over h is equal to 1. As it turns out, for b equals e, Euler's number, which is approximately 2.718, we have that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. This is by the definition of e. So, if f of x is equal to e to the x, then f prime of 0 is equal to 1. Remember, that limit that we were cranking on was f prime of 0. And we get that the derivative with respect to x of e to the x is e to the x. Probably the easiest derivative we'll ever see. Of course, we always have things of making more interesting, and so we'll say the chain rule applies as appropriate. So the derivative with respect to x of e to the u of x, where the exponent is a function of x, we have e to the u of x times u prime of x, where that u prime is coming about because of the chain rule. So for a quick example here, if we let y equal e to the x squared, and if we're asked to find y prime, then y prime will be e to the x squared times the derivative of the inside function here. So 2x e to the x squared because of the chain rule. And that would do it for that. But I'm going to continue with this exercise here and say now we're going to find y double prime. At this point now, we have a product. I'll just rewrite that y prime is equal to 2x e to the x squared, and 2x will be u, and then e to the x squared will be v. And if u is 2x, then u prime is 2. If v is e to the x squared, then we just saw that v prime is going to be 2x e to the x squared. And just a minute, I almost forgot to remind us of the product rule. The derivative of the product uv is equal to u prime v plus uv prime. You probably just heard that this is an edit, and so this is about to disappear from the screen, so make sure you have it written down. And now we're moving on. And so our derivative is going to be u prime v, and so 2e to the x squared plus uv prime, and so 4x squared e to the x squared. Now, how do we know that Euler's number is approximately 2.718? Let's explore that, and then we'll be done with this particular video. Suppose that e can be represented as 2 to the c, some power of 2. And we know that this is possible because an exponential function is continuous, and if I have y equals 2 to the x, then we go through the point 0, 1, and at some point I'm going to cross through the value that we think is e, e being approximately 2.718. So it is reasonable that there is some input value for which 2 to the c is equal to e, some value of c, right? So if e is 2 to the c, then e to the x is 2 to the cx, right? Just raising both power to the exponent of x. Now we're going to differentiate. On the left, we already saw that we had e to the x. And then on the right, we have the constant, I'll call it k, times c times 2 to the cx. And this c here is coming out because of the chain rule from the cx exponent. This k is the limit that we saw earlier, the limit as h approaches 0 of 2 to the h minus 1 over h. Now, if we let x equal 0, then on the left-hand side, we have 1, and on the right-hand side, we have k times c. This is great because since we know what k is, we can solve for c and figure out what it is. We can see clearly that c is equal to 1 over k. So now that we have a value for c, 1 over k, we can make that the exponent on 2 in that equation that said that 2 was equal to e to the c. Therefore, e is equal to 2 to the 1 over k. And using the value of k, 0.693147, just a little more accurate than the last one we wrote down, we can see that e is approximately then 2.718282357, where we're accurate up to maybe about the 1828-ish. And if we needed to be more accurate, we would just have more decimal places for the value of k. So there it is, the derivation of Euler's number e. And we'll wrap this up by saying that since the derivative with respect to x of e to the x is equal to e to the x, I'm going to put that in a box because it's an important result. We're going to keep going. It follows that the integral of e to the x dx is equal to e to the x plus a constant. So that's a 2-for-1 special. We got not only a differentiation formula, but an integration formula as well.